It's my pleasure to introduce you our today's speaker, Dr. Igor Khramtsov from Center for Photonics and Two-Dimensional Materials of Moscow Institute of Physics and Technology, with a talk on optoelectronics of color centers in diamond and silicon carbide. So before Igor starts, let me remind you the rules of the seminar. If you have any questions, please ask. You may raise a hand, and then I will let you ask, or you may directly ask the speaker by voice, but please make sure not to interrupt him just in the middle of the sentence. So Igor, please, the stage is yours.
Okay, thank you, Maxim, for the introduction. Yes, I have recently received PhD degree, and this talk will be mainly about my PhD thesis that I was doing in the MIPT under the supervision of Dmitry Fedyanin. Okay, today, firstly, I will introduce you into the topic of the single photon sources and outline the corresponding problems with single photon sources. My main part of the talk can be roughly divided into two parts. The first one is devoted to the second order autocorrelation function, and the second one is devoted to the bright electroluminescence of color sensors and electrical pumping. And in the end, there will be a summary. So implementation of various applications of quantum physics ranging from secure optical communication lines based on quantum cryptography to linear optical quantum computers requires sources of non-classical light that are able to generate a train of single photon pulses that contain strictly one photon per pulse. And any quantum system capable of emitting a single photon sources is suitable for the role of single photon source. For example, one can use two-level system that has radiative transition between the excited and ground state, and has the possibility to repump it back from the ground to the excited state. And from the first observation of the single photon emission in 1977, various quantum emitters were proposed. These are the defects in carbon nanotubes, single ion, single molecules, quantum dots, but the most promising are color centers in diamond, silicon carbide, and other wide bandgap semiconductors that are point defects in the crystal lattice of the corresponding semiconductor. Color centers combine the properties of isolated atoms and solid-state sources, and unlike quantum dots, exhibit remarkable optical and spin properties at room temperatures and above. The slide shows the most studied of them, a nitrogen vacancy color center in diamond, which comprises of nitrogen atom that replaces the carbon atom, and the vacancy is the absence of the carbon atom. Color centers give color to the colorless diamond, because if we take a defect-free diamond, it has no energy levels in its band gap. That's why it doesn't absorb the optical emission. And but color centers have the energy levels in the band gap that absorb and emit light in the optical part of the spectrum. The first work on the single photon emission from color centers in diamond appeared 20 years ago, and in order to pump the color center from the ground state to the excited state, a bulky laser was used, namely a laser with a wavelength of 532 nanometers. And it was shown that at room temperature, color centers in the bulk of the diamond emit more than 400,000 photons per second. But if one put color center into a nanoresonator, it emits one order of magnitude higher. For comparison, the quantum dots at room temperature emit less than 8,000 photons per second. And however, from the practical point of view, optical pumping is not promising. Instead, it's better to use an electrical one when we take our diamond diode and pass the current through it, because there is no need of a bulky external optical source. There is no need for the pumping filtration. Moreover, we can take a lot of our single photon sources, millions of single photon sources, and put it on chip and bypassing the current, efficiently excited and emit photons. However, electrical pumping of color centers in wide bandgap semiconductors is difficult, since these materials are at the interface between insulators and semiconductors. This led to the fact that the first work on single-photon electroluminescence of color centers appeared only 10 years ago, and the results under electrical pumping were different from that under optical pumping. For example, the brightness of the defects under electrical pumping was 1 order of magnitude lower than under optical pumping. Moreover, for example, NV center can exist in 2 different charge states. It's NV0 and NV-. And also during the photoluminescence, that is the optical pumping of color sensor, researchers have obtained both spectrum from NV0 and NV-. Under electrical pumping, only NV0 was obtained. Moreover, an interesting effect was discovered. The characteristic time of G2 function varied from 10 nanoseconds to microseconds under electrical pumping. However, under optical pumping, it stayed almost constant in the range of 10 nanoseconds, and the nature of this effect was not clear. Here you can see one of the 2 first papers on single-photon electroluminescence from color centers in diamond, mainly from NV centers, that was put into the PIN diamond. So P-type diamond doped with acceptors, I diamond is undoped layer, and N-type diamond is doped with donors. So typically in the experiments on single-photon sources, researchers are interested in 2 parameters. The first one is G2 function, and the second one is the electroluminescence rate, that is the brightness of our color center. It shows how many photons, single photons, are emitted per second. And yes, the color centers can be isolated with the confocal microscopy and obtained single photon emission. In all single photon experiments, the Henbury-Brown Twist scheme with 2 detectors is used to prove single photonity. The emission under study goes through the beam splitter to 2 detectors. Then first detector clicks. The time needed for the second detector to be clicked is calculated, and the time diagram is plotted. It can be shown that this time diagram corresponds to the G2 function. And in the experiments, the researchers are interested only in the value at tau equals 0, because if G2 at tau equals 0 is less than 0.5, then the emission under study is single photon. However, the shape and characteristic times of the G2 in the cases of optical and electrical pumping from the same color center differ. Thus, it's important to learn how to extract information from them. And in order to do it, let's look at the first model of the electroluminescence that explained some previous results and had predictive power. This model was published by my supervisor with his colleague in 2016. And the idea is the following. While in the case of the photoluminescence, we can treat color center as an isolated atom that almost does not interact with the surrounding crystal, maybe except for the phonons that just broadens the spectrum. In the case of the electroluminescence, the interactions with the crystal became important. So let's consider the NV center that has 2 charge states, and the process of the electroluminescence is cyclic. Let's start from the ground NV0 state. So being in this state, the color center captures an electron from the conduction band that brings the system to the ground NV- state. Then the system captures a hole from the valence band that brings the system to the excited NV0 state. Then the system relaxes to the ground state, radiatively or not. It depends on the quantum efficiency of the color center. That returns the system to the initial state, and the cycle begins another one time. This model allows to answer why there is no NV- part of the spectrum in the electroluminescence spectrum from NV centers. The idea is that according to the energy conservation law, the electron at the bottom of the conduction band cannot give the system such amount of energy to bring it in during this capture, bring it to the excited NV minus state. Therefore, it can be brought only to the ground NV minus state, and there is no radiative transition during the electroluminescence cycle from the NV minus state. Okay, now we can use this model to describe the G2 function. Since the photon emission probability is proportional to the excited state population, it can be shown that the problem of finding G2 function is reduced to the problem of finding the time dependence of the population of the excited state and the initial conditions that right after that at the time tau equals 0, the color center is in the ground state right after photon emission process. And in this case, G2 function became just the ratio between the excited state population of the excited state normalized to some constant, which is the steady state population of the excited state. Since the dephasing time, for example, due to the collisions with acoustic phonons, is in the order of picoseconds, and the characteristic time of the G2 function is in the order of 10 nanoseconds, we can write down classical rate equations in order to find the populations of the excited state. There's no need for the Liouville equation on the density matrix. Yes. So I solved this system of equations and obtained the following.
So, Igor, can I ask a question about this system just on the previous slide?
Yes.
Yeah, so what are the coefficients EP and EN correspond to electron? So I do not see them on the picture.
Ah, yes, the EP, ER, and EN, it's the let's say thermal excitation from the excited ground states. For example, if the hole is captured, it also can be thermally excited back to the conduction band. Mm-hmm. And yes, we have these coefficients that are actually very low, and eventually at the photon emission rate above 1 photon per second, which is actually very low, we can just neglect these coefficients.
And so the indices, so the lower indices P, R, and N stand for what?
Okay, let's look at the the X is the population of the excited state. Mm-hmm. So what can be done? We can capture the hole, which is Cp times P times 1 minus X minus F. Mm-hmm. We can then thermally release the hole from this state. It's proportional to the excited state population. Then we can obtain, let's say, we can, let's say, obtain electron from the ground state. It's ER. This is proportional to the ground state population. And then we can, there is also radiation.
But this is basically like relaxation. It's not dephasing, it's just relaxation.
Yes.
Mm-hmm.
The dephasing time is needed to prove that we can write down classical rate equations.
Mm-hmm. Mm-hmm. Good. And so in the second line, we are writing the same things for population of the valence of this ground state, yeah?
Yes. For the ground state, yes, we can release an electron.
Mm-hmm.
Yes, we can receive an electron from the NV minus ground state. We can release an electron. We can, yes, and because we have an electron capture, and so because the system goes from this state to this state, and we have some transition, right? Mm-hmm. So maybe I haven't said Cp times P is the hole capture rate, and Cn times N is the electron capture rate. So Cn is the constant that can be calculated theoretically. N is the electron density in the vicinity of the color center, and Cp is the same. Also can be calculated theoretically.
So this means that you have like two equations, linear differential equations with respect to x and f. You have some kind of exponential relaxation, maybe 2 exponents at maximum.
I will show later.
Clear. Yeah, good. Thank you.
Okay. So yes, I have received this expression for the G2 function, which that looks similar to the optically pumped three-level system, because it has also the exponential term responsible for the bunching, and it has also the exponential term responsible for the anti-bunching. And these parameters A, tau1, tau2 depend on the diamond material parameters, lifetimes of the energy levels of the color center, like in the case of the optically pumped three-level system. But unlike the optically pumped three-level system, it has the dependence of the electron and hole densities in the vicinity of the color center. Yes, you can see that we have this Cn times N, Cp times P in the expressions for A, tau1, tau2. Oh, there is a back, sorry. There is no line here. Okay, yes, and it really depends on the electron and hole density in the vicinity of the color center. I just plotted G2 at different NP, and it can be seen that the width can be varied by varying NP near the color center. And at moderate currents through the diode, the expression for G2 function can be simplified to the one exponential dependence, and the tau2 parameter will be 1 divided by Cn times N plus Cp times P. And in this case, we should remember that the electron is captured by the neutral NV center, but hole is captured by the negatively charged attractive NV minus center. And therefore, the hole capture constant should be much higher than electron capture constant. And also, in the case of diamond, electron density does not exceed the hole density, as can be seen, for example, from this insert in the panel A. Here we see that the electron and hole densities in some point near the color center equals each other. And what we obtain that tau2 is just 1 over Cp times P. And in this case, we see that dynamics of the single photon emission of color centers in diamond and electrical pumping, that is characterized by G2 function, is determined by the hole capture process, which rate is proportional to the hole density. And thus, we propose a new method of determining the local hole density. What we need to do, we need to measure G2 function from the color center and measure the deep width of the G2 function. So after it, we can just divide by Cp and obtain the hole density near the color center.
So, Igor, may I ask a question? So I wonder whether there is any dependence on the type of the color center. So
yes,
it sits.
There is a dependence, but for example, this theory can be almost the same for the. Okay, now it's written for the NV center. For example, for the Silicon-vacancy-center, the second study center in diamond and overall, we will have almost the same, but we have to change N and P coefficients and also change the N and P. So in this case, the expression will be the same because it's symmetrical over the NP changing. Why it happens? Because for CV center, I will show the electroluminescence model. Yes, for example, for the CV center, we have CV minus here. We have a radiative transition from the CV minus, but have no radiative transition from the CV0, but the system, but the electroluminescence process looks similar. For other color centers, for example, in other materials, yes, sometimes other charge states takes part in the electroluminescence process. But what I want to say is that doubly charged states doesn't take part in the electroluminescence process, because the probability of capturing an electron by the negatively charged NV- center is very, very low, because it's not an attractive potential, and the electron doesn't want to be captured by NV- center. Yes. Yeah. Okay. Next, we decided to test the obtained theoretical approach in practice and reproduce the recent experimental results on the measurements of the G2 function and electrical pumping. At that time of this study, there were actually two works, and only one of them contained all needed parameters of the diode used. And those parameters that were not known do not affect the G2 functions. Since the electroluminescence process depends on the electron and hole density in the vicinity of the color center, I have performed the stochastic simulation of the electron and hole transport in the PIN diode that corresponds to the experimental diode, and using the theoretical approach that was developed, reproduced the G2 function at different currents through the diode, and then compared to the experimental result. It can be seen that the predicted G2 functions reproduce well the experimental ones at different pump currents. Moreover, they explain the strange behavior of the deep width, the strange dependence on the current, which was previously unknown. Since, as I said, one diode parameter, namely the donor compensation ratio in the n-type layer, was not known, it was impossible to reproduce the dependence of the single-photon electroluminescence rate on the current, on the G2 function. But for the color center in silicon carbide, there was an article. Actually, it was there was only one article on single-photon source in silicon carbide. And this article, the authors of this article provided us all the information that we needed to perform the simulation. And in this case, we were able to reproduce not only G2 functions at different currents, but also the dependence of the single-photon electroluminescence rate on the current density. Moreover, we predicted the self-heating effect that was later confirmed by the authors of this experimental paper. Okay, let's continue with the second part of my talk. For practical application, it's important that our color center is as bright as possible, and single-photon electroluminescence rate is determined by the expression shown on the slide. It has the what does it have? It has the quantum efficiency phi. It has the electron and hole capture rate, and it has the excited state radiative lifetime. And in the case, and yes, the higher the electron and hole density in the vicinity of the color center, the higher its SPL rate. So the brighter the single photon source based on the color centers in diamond and also in other wide bandgap semiconductors. In the case of diamond, the electron and hole capture rates are very low, and we can neglect this term, the excited state radiative lifetime, and obtain the following expression. Also, as I have already said, we have some inequalities with Cn and Cp, which eventually allows us to simplify the expression to just quantum efficiency times Cn times n. And now we should remember with what material we are working. We are working with diamond, which is one of the wide bandgap semiconductors. And in almost all wide bandgap semiconductors, there is a asymmetry in doping. What does it mean? It means that in the case of diamonds, we cannot create high density of electrons. Why? Because first of all, the donor ionization energy is 0.57 electron volts, that is almost 22 kT at room temperature. For comparison, in silicon, the donor ionization energy is only 45 milli-electron volts. Also, when one tries to dope diamond layer with donors, it inevitably creates a significant amount of compensating acceptors. And the donor compensation ratio shows how many of acceptors is created. And typically, in the experiment, the people can dope diamonds with a donor compensation ratio of from 4 to almost 90%. And if we look at the dependence of the electron density in the N-type diamond on the donor compensation ratio, it can be seen that at typical experimental values of the eta n, the electron density doesn't depend on the doping level and is determined mainly only by the compensation ratio, usually not exceeding 10 to 11 per cubic centimeter. And if we take now a typical PIN diode that is used for the single-photon electroluminescence and make the following assumption, that since electrons are injected from the N-type layer into the I-type region, there is the color center, we can assume, it's obvious to assume that the density of electrons near the color center doesn't exceed the equilibrium density of electrons in N-type layer. And in this case, we can write down this inequality. And if we now plot phi times Cn times n in equilibrium as a function of the donor compensation ratio, we can see that for the range of typical compensation ratios, the single-photon electroluminescence rate will be no more than 1,000 photons per second. And it's very low for practical application. In this case, we should remember that this is just the number of photons that are emitted by the color center. After it, photons should be collected, and actually, typically, the collection efficiency is almost 5%. Only 5% of photons are collected into the objective. So let's see how can a high density of charge carriers is created in other optoelectronic devices. And the solution for which Jared Alfer received the Nobel Prize is the superinjection effect in double heterostructures. If one puts a semiconductor with relatively low band gap between two semiconductors with relatively high band gaps doped with acceptors and electrons, and pass a current through this diode, the electrons and holes will accumulate in the corresponding potential wells for the electrons and for the holes. I took some double heterostructure diode with gallium arsenide and aluminum gallium arsenide and performed the simulations and show that the electron density in different points of the gallium arsenide can be 1-2 orders of magnitude higher than the equilibrium density in the aluminum gallium arsenide. However, from the discovery of the superinjection effect in double heterostructures, it was considered that it's possible only in double heterostructures. However, there is no any successful experimental realizations of double heterostructures with diamond. What shall we do? Now I will show that the superinjection effect do exist in PIN diamond common structures. Let's take a typical PIN diamond diode with typical parameters of concentration, dopant concentration, ionization energy, compensation ratio that corresponds to the experimental diode, and look at the band diagram for this PIN diode at different voltages, price voltages. At low bias voltage of 4.4 volts, this is just a typical band diagram with the conduction band edge and the valence band edge. But when we apply higher bias voltages, a potential well for electrons appears in the I region. And in this potential well, electrons tend to accumulate, which can be shown from the electron distribution at different currents. It can be seen that the electron density can be 10 to 14, which is 3-4 orders of magnitude higher than can be obtained in N-type region during the doping. And now we should remember that the single-photon electroluminescence rate in the diamond diodes depends mainly on the electron density. And if we plot now the dependence of the single-photon electroluminescence rate on the position of the color center within the PIN diode, we can see that for the color centers located here near the potential well, this color center will emit more than 3 millions of photons per second. Is much better because it's 3 orders of magnitude higher than the doping limit in quotes. You can see that the results are counterintuitive because the high electron density appears near the PI interface and not near the NI interface. And these results allow us to explain the failure of recent experiments on the electroluminescence of silicon-vacancy-centers in diamonds. So also the electroluminescence of silver centers was shown. It was shown only for the ensemble of silicon-vacancy-centers, not for a single silicon-vacancy-center. Moreover, the single-photon electroluminescence rate was 1 order of magnitude lower than for a single NV center. But if we take into account that it was only from the ensemble, it means that from a single silicon-vacancy center, it was even lower. But why? Let's now look at the dependence of the silicon-vacancy center SPL rate for the center that is located near the NI interface, the dependence on the current. It can be seen that the maximum SPL rate will be no more than 300 photons per second. And if we take into account different collection efficiencies, we obtain at the photodetector only 15 photons per second. That was quite impossible to detect because of the detectors that was used, because of the detectors that were used in the experiment. But if one puts the silicon-vacancy center near the PI interface, its SPL rate will be at the photodetector site will be more than 8,000 photons per second, which that is very interesting and can be detected by single photon detectors. And it can be seen that actually TV center and actually any other color centers should be located at a distance of 200, 500 nanometers from the PI interface. And also there are current regimes that should satisfy our device in order to obtain high brightness from the color center and electrical pumping.
So Igor, may I ask a question about this previous slide? Yeah. So I wonder whether we can explain this effect here in terms of, let's say, parcel effect. So depending where you put this silicon vacancy center, you get different field at this center and then like different intensity emitted by it. So can we try to explain in these terms?
This is just because of the electron and hole distributions. And the higher the electron and hole distribution near the color center, the faster is the electron and hole capture processes. The center tends to change its charge state faster, and this is just because of it.
So the whole game is around the density of electrons and holes, which depends on Z, and then you get different. Clear. Thank you.
Okay, we have also studied the superinjection effect inside and out and found out that, for example, the wider I regions of the p-ion diode results in the high SPL rate. However, very wide I regions act as a resistor, and if one wants to obtain the same brightness of the single photon, the same brightness of the color center at wider I region, it should apply high bias voltages that might be not suitable for the on-chip technologies. We have also found that the physics of the superinjection effect is based on the correlation between the drift and diffusion components of the electron current. It was also found that the superinjection effect can also be observed with poor contacts to the N-type diamond, because in the diamond community it is well known that the contacts to the N-type diamonds are very poor. They are characterized by the high contact resistance. But anyway, it can be seen from this plot, the dependence of the maximum SPL rate on the current density stands the same for different contacts. It doesn't depend on the type of the contact. It's the same and for the ideal only contact and for the bad Schottky contact with a barrier height of 2.5 electron volts. And yes, but the idea is that bad contacts results in the higher voltages that should be applied. For example, for the bad contacts with the Schottky barrier height of 2.5 electron volts, the one should apply voltages above 80 volts. It is not suitable for the on-chip technologies. We should deal only with volts something near 5 volts or so. Okay, in diamond, where there are problems with electrons, the superinjection effect of electrons exists. But in the case of other wide bandgap semiconductors, where there are problems with holes, the superinjection effect of holes allows to inject 2-3 orders of magnitude of holes more than can be created in the p-type layer. It's the same as for diamond, but for holes in other wide bandgap semiconductors. And also the holes tend to accumulate near the I-N interface that is counterintuitive. Also, by the way, superinjection effect in the p-ion diode has some problems. For example, the superinjection area is very small compared to the whole I region. For example, you can see from the electron distribution at different voltages. Here, the I region has a width of 10 micrometers, and the superinjection region is only one micrometer. And in order to solve this problem, we propose the p-pin diode. It's a p-ion diode with IP grating in the I region. IP grating consists of I region with the width of 400 nanometers and p-type region with width of 200 nanometers, and the whole I region is 10 micrometers. I won't go into details, but the idea is that IP grating allowed to increase the superinjection area, it also increased the total number of injected electrons, and created areas in which color centers will exhibit almost identical emission properties. You can see the comparison of 3 diodes: pin diode, p-pin diode with 3 IP gratings, and which is the blue line, and the red line stands for the p-pin diode with 6 IP gratings. And the last part of my presentation is devoted to the aluminum nitride diamond heterostructure. Previously, I said that it's hard to inject high electron density from the N-type diamond layer. Of course, one can use superinjection effect in order to inject 10 to 14 electrons into the I-type diamond. But what if we want more? 1.5 years ago, we realized that there had been experimental attempts to create aluminum nitride diamond heterostructures, and aluminum nitride has a lot of electrons. By the way, it has a very low number of holes in the p-type aluminum nitride, but we will use n-type aluminum nitride. What if to use this n-type aluminum nitride as an electron injection layer? Eventually, we have proposed the diode that you can see on the side, and found out that the electron density in the I-type diamond can be more than 10 to 16 per cubic centimeter. At the same time, that is 2 orders of magnitude higher than can be obtained in the superinjection effect. At the same time, the hole density in this region also very high, 10 to 16 per cubic centimeter, that should result in high SPL rate for the color center located here. And yes, if we put Silicon-vacancy-center here in this I-type diamond and look at its dependence on the dependence of its SPL rate on the current density, we can see that it can be as bright as 3 million photons per second. I also have a comparison with the p-ion diode with superinjection effect, which is the gray line. It can be seen that the CEVA center is dimmer in the case of the p-ion diamond diode. These are very interesting results, but the problem is that the aluminum nitride and diamond have a bit different lattice constants that leads to possibly high density of interface recombination centers. Here you can see the distribution of electrons at the interface between the aluminum nitride and diamond. And if there is no recombination centers, the electrons in diamond has a very high density. But if we put interface defects, they can capture electrons and holes from both aluminum nitride and diamond, that eventually leads to the very low electron density in the diamond. And our single-photon source will be very dim. That can be seen from the right plot. And the conclusion is that the higher the density of the combination centers, the lower the electron injection efficiency and the lower the maximum SPL rate. Therefore, further experimental research on this topic is needed. Okay, that brings me to the end of my presentation. In the end, I want to summarize my talk. We have proposed a theoretical approach for the qualitative and the quantitative description of the dynamics of the single photon emission of NV centers in diamond and electrical pumping, and use it to reproduce recent experimental results. This approach can be easily adapted to study other color centers that we have shown for the other color centers in silicon carbide. We have theoretically predicted and numerically demonstrated the superinjection effect in diamond p-ion diodes, which was previously considered to be possible only in heterostructures. This effect allows to accumulate in the I region of the diode an atypically high electron density for diamond devices, more than 2 times 10 to 14 per cubic centimeter, and as a consequence, to increase the brightness of color centers and electrical pumping by more than 3 orders of magnitude, up to several million photons per second. It has been shown for the first time that the observation of bright single-photon electroluminescence from color centers in p-ion diodes only possible when they are located in the I region at a distance of about 200–500 nanometers from the p-I junction, and not near the I-M junction, as should be done based on intuitive considerations. We have also proposed the possibility to control and enhance the effect of superinjection in diamond p-pin diodes, and we have proposed and numerically demonstrated bright SPS-based single-photon sources based on aluminum nitride diamond heterostructure, and yes, the SPL rate can be as high as 3 million photons per second. Okay, thank you for the attention. I'm glad to ask questions.
Thank you very much, Igor. A very nice talk. So the talk is open for questions. Colleagues, if you have any, please raise your hands just to be visible. So in the meantime, I have the first question. Discussing this single photon emission from the color centers, I wonder whether the purity of the sample, so the existence of some defects nearby, affects this single photon emission, and if so, how it deteriorates, let's say.
Yes, surrounding defects will give rise to the background of the emission. And also the emission from the background is not correlated with the emission from the color center, and it eventually leads to the problems with different quantum applications. But what to do is just to anneal the sample in order to low down the number of defects. And yes, people can do it and make the sample such that they focus only on one color center and there is no anything around it. And they collect the emission only from one color center.
Mm-hmm. But how do you see that from experimental data? How this is manifested in, let's say, data for G2 correlation function? Are there any characteristic signs?
For example, if you look at the G2 function and you have a very noisy, not noisy, but you have a lot of background emission, you will see that at the G2 at 0 time delay will be higher than 0.5. For example.
Thank you.
And also from the spectrum, you will see different peaks, and yes, that can correspond to different other color centers. For example, if you are, for example, in the case of diamond, the nitrogen is the main impurity even for the natural diamond, and you always can have these NV centers in natural, even in natural diamonds. And for example, if you want to create silicon-vacancy-center and you haven't thought about how to deal with NV centers in the spectrum that you will collect, you will see both lines from CV center and NV center.
Right. So I see another question from Roman. Roma, please.
Yes, thank you. Thank you for the talk. Can you hear me well?
Yes, we can hear.
Yeah. Okay. So I have a question, maybe a general question. Do I understand correctly that if you use electrical pumping, you can only use it with like layer of the diamond, not some nano diamonds or some structured diamond films, something like this?
Yes, for example, you cannot use nano diamonds that are actually studied in the case of optical pumping because they act as nano resonators, and you can obtain bright emission from the color centers in nano diamonds. It's impossible to create contacts to nano diamonds. You have to have, let's say, white regions in order to place contact. But anyway, maybe in the future there will be a possibility to deal with diamond diodes with small sizes. For example, 1 electron transistors or so, or transistors, they exist. So why not do it with diamond? But the diamond is very hard. It's hard to cut it. It's hard to create structures with diamonds. People are struggling with it.
Okay, I get it. Thank you. And also the question about the collection efficiency. So you showed that was like of the order of several percent. Is it like always like that when you deal with electrical pumping? Can you improve it somehow?
Yes, you can improve it by using some nano antennas. My supervisor is developing the nano antenna that can absorb, I don't remember the numbers, but maybe the collection efficiency is more than 80 or 90%. But if you just take a confocal microscopy and focus on the Hall center in, let's look at the experimental figure. Where it is. Yes. Yes, here. If you deal with in the experiment, if you just focus with confocal microscope, like in this top left figure, you will obtain only several percent of collection efficiency due to the high dielectric constant of diamond and due to the internal reflection.
Mm-hmm.
That's why, and also there is a dependence on the let's say directivity of the dipole of the, for example, the center, because it has a linear polarization, and if we change the orientation of the dipole relative to the surface, we will have different collection efficiency. They will differ maybe by a factor of 2, but anyway, it will be only several percent. You have to think about it very carefully.
Okay, thank you. Thank you.
So maybe one more question from my side. So you mentioned in the talk that dephasing effect in these systems is much stronger than the relaxation rate. So let's say dephasing times around picosecond scales, which allows you to use classical rate equations. So I wonder whether it is always the case when you are dealing with NV centers, or there are some ways to increase dephasing time.
I don't know if it's possible to increase somehow, but it's usually the case that the dephasing time is much lower than the characteristic time.
Yeah, but maybe the question in the time scales, because when people are saying, okay, we will make a qubit out of that and so on and so forth, still you have to somehow store the coherence information for more or less appreciable time. Otherwise, you cannot use this for qubit applications. So it looks like...
Yes, it looks like that picoseconds is not what we want from a qubit.
Absolutely.
But people somehow deal with it, but they use... yes, I don't remember, but people, as far as I know, the NV center has maybe microsecond dephasing time for some system, but I don't remember. But
because microsecond, it's another story. Yeah, it's another story,
even
because superconducting.
And even in milliseconds from the Hall center. But in the case of yes, if you want to increase the dephasing time, you have to know how to control the charge state of the Hall center, because then it changes it decreases the dephasing time. Yes.
Clear. Yeah, that's interesting because nowadays everyone is speaking about these quantum applications. So very nice talk. Thank you very much, Igor. I do not see any other questions from the chat. So I assume we thank you for